IEEE SSCS Oregon Chapter first event of the year. And we're really grateful to the San Diego chapter for hosting this event for us on short notice. And then we're also tried to also get the Seattle chapter to be sort of coming along for the ride as well. So we have 3 chapters all sort of collaborating together on this talk. And, you know, we're really happy to kick off the talk with a really good talk by Stefano Pellerano. A little bit about the chapter itself. So if you can move to the next slide.
Yes.
First, first start off with the Solid State Circuit Society. The Solid State Circuit Society, we really, if you're not a SSCS member, really encourage you to become an SSCS member. We have lots of free stuff. We have educational career development. We have networking with peers, leadership opportunities, and we have tools for career growth. We have a lot of free educational materials. You can find all of this great stuff on sscs.ieee.org. And you know, it's a very low cost, $11 for IEEE members and just $5.50 for IEEE student members. So really encourage all of you to become SSCS members if you haven't done so. If you can please move to the next slide. So the next slide introduces our chapter executive committee. I'm the chapter chair, and Richard is the chapter vice chair. He gets to organize a lot of the events for us and puts the schedule together. Lee is the treasurer, and Xiaoshan is the chapter secretary. And you know, we were reactivated in 2017, and we've been fully active since 2018. Normally we would do this in an in-person event with pizza and drinks, and typically it's been every first Wednesday of the month. We're adjusting the schedule a little bit to make sure that we get more folks to attend, so maybe a little bit earlier in the afternoon before you have to go home to be with the family. And typically we do giveaways at our events with some SSCS goodies. And we've also had our first social in December, and we look forward to more in-person socials, hopefully by the end of this year. And now I'm just going to hand it off to Stefano, who's going to talk to us. And Richard, do you want to introduce Stefano?
Yes, sure. Stefano Pellerano received the Laura degree and PhD degree in electronics engineering from Politecnico di Milano, Milan, Italy in 2000-2004 respectively during his PhD. His activity was focused primarily on the design of fully integrated low power frequency synthesizers for wireless applications. In 2003, he had been a consultant with Agar Systems, formerly Bell Labs, in Allentown, Pennsylvania. And since 2004, he's been with Intel Labs in Hillsboro, Oregon. He's now a principal engineer leading the next generation radio integration lab, where he drives several research activities focusing on enabling radio circuit integration in deeply scaled CMOS technologies. His main research contributions have included MIMO transceivers for Wi-Fi, digital PLLs, high efficient digital architectures for polar and outphasing transmitters, millimeter wave radio transceivers and phased array and low power systems. For the last few years, he's also been exploring cryogenic CMOS integrated circuits for qubit control and fault-tolerant scale quantum computing, which he'll be giving us a talk here today about. So Stefano, if you want to take it away.
Yes, thank you. Thank you, Richard, for the introduction, and also thank you for the opportunity. So today, as Richard already anticipated, I would like to give you an overview of quantum computing in general, and also show you why I think that the classical IC design and integration is actually a critical component for the development of a fault-tolerant scalable quantum computer. So let's see if we can advance this. Okay, so legal information, done with that. So acknowledgement first, I want to say that, of course, this work was only possible with collaboration of many people within Intel Labs, and also Component Research, which is another big org at Intel. And of course, thanks to the colleagues and collaborators at TU Delft and QTAC in the Netherlands, with whom we've been collaborating on this topic for more than 5 years, as you probably know already. Okay, so let's dig into it, and let's first look at some of the basics of quantum computing. I think this is useful. Some of you might already know some of the basics. So let's look first at some of the key concepts of quantum computing. So the first one, in my opinion, is superposition. And you might be aware of this. So in classical physics, we can represent, for example, the state of a bit, like a classical bit, for example, as a coin. And so it can either be 0 or 1. So the coin can either be a head or tail, as is like sitting face flat on your desk. In quantum physics, instead, the quantum bit or qubit can actually be 0 and 1 at the same time. So, and the nice thing about the coin is that you can see this as a coin spinning on the table. And so it's basically heads and tails at the same time. The other concept, which is also extremely powerful, is entanglement. So, and as you can see here, basically a quantum state of a system cannot be factored as a product of states of its individual local constituents. So what this means is that if we have, for example, n entangled quantum bits, this represents a total of n, 2 to the power of n states. So I just want to give you an example. Imagine that you have, say, 48 entangled qubits, and you want to do like a quantum simulation of this system on a classical computer. And again, since the state of the qubit is not 0 or 1, but can be anything in between, if you use, for example, 8-bit precision to express or represent a quantum state, it means that for this system, you need 2 petabytes of memory. So it's already show how difficult it is to simulate a quantum system of only 48 qubits. And this entanglement is what you probably know Einstein called the spooky action at distance, referring to the phenomenon when you entangle 2 qubits and then you go and then discover or measure the state of 1 qubit, the other entangled qubit state is immediately defined by this measurement without no time delay, no matter what the distance between the qubits is. So applications, there are of course many different applications, but the bottom line here is that with the quantum system, because of the entanglement and superposition, you can have an exponential speed up compared to a classical algorithms for some specific applications. So depending on how many qubits you have entangled, applications becomes more and more relevant. For example, for 50 qubits, you already have, as we said before, more state than any possible supercomputer. And this means that you can potentially already demonstrate quantum supremacy, meaning doing something with a quantum computer that would take longer to do with a classical computer. And this is what Google demonstrated already recently. When you have 300 qubits, this, if you think in terms of state, is already more states than the atoms in the universe. So this is something that always makes me think. And when you reach, say, 1,000 qubits, even if we don't really have, or you have a very limited error correction, you can really solve quantum chemistry problems, you can address quantum neural networks, and you can really do some complex optimizations. Then when you get to the holy grail, meaning, say, 1,000,000 qubits and full error correction, you can start doing, factoring, cryptography, and structure search, and really solve large linear systems. And so starts really solving not ad hoc problem built for the computer, but something that is actually useful. And in fact, physicist Richard Feynman was the first to propose the use of quantum computing to simulate anything that is quantum mechanical in nature. And so basically to do a simulation of nature, as it could be very powerful, for example, for chemistry. Now, the last concept is fragility. And this means that a quantum state collapses to a classical state if disturbed. And disturbing means, for example, measuring. You observe the qubit, you go and measure it. You're not going to measure something between 0 and 1, but you're going to be measuring always 0 or 1, of course, with a certain probability. But this is not just measurement, it could also be noise. If the system is coupled with noise sources that could be like thermal noise or anything else, radiation, you can actually collapse the qubit to a classical state. So to address this problem, one vision is to have a way of detecting this error by using this, so-called ancilla qubits that are coupled and are able to show that the error happened, and then you can keep track of this error and take it into account into your algorithm. But this means that in order to have like one logical error protected qubit, you need to have many physical qubits that are not perfect. And so this actually is one of the reasons why today we don't really have a quantum computer. So now that we've seen, the basic, let's see what we need for actually building a quantum computer. In this very interesting paper, DiVincenzo defined what the criteria are to build a quantum computer. And so, first of all, we know we need a qubit that can be addressable and it's well defined. We'll talk more about this in a moment. Also, this qubit has to be initialized in a state that we know for sure. For example, we should be able to put it in a ground state. The qubit decoherence time has to be large or long. And what does this mean? It means that if we have some gate operation time or some time required to operate on the qubit, the coherence time of the qubit has to be much longer than this gate operation time. Otherwise, by the time we start operating on the qubit basically dies. And you can see this decoherence time as like, a free-running resonator, and you want very high quality factor. You also need to have a universal set of gates, and this is basically to build your logic and build your computer. And last but not least, you need to have a way of reliably measuring the qubit state. So a way of measuring the qubits. Okay, so now let's look at the qubit, which is the quantum bit. So as you probably know, a quantum bit can be implemented with any two-level system that manifests quantum mechanical behavior. And so when we implement this, we can use different, physical implementation. For example, one of the most common and more reliable, in my opinion, today is the Transmon qubit or superconducting qubits. So this is based on a non-harmonic LC oscillator. So it can be macroscopic, and you can control with microwaves. We can couple with micro lines. You can build circuits, and you use as the qubit level basically the lowest energy levels of this quantum oscillator. These are, for example, the qubits that are used by Google, IBM, Rigetti, and D-Wave. Another type of qubit is implemented using trapped ions. So this is effectively using energy levels of an ion, of a metal ion, typically. The energy gap for this levels it's larger than, for example, the case of Transmon. So you need a higher energy photon here. So you actually go into the optical domain. So you need laser to manipulate these qubits. And this is, for example, the qubit that are used by Honeywell and IonQ. Then we have the silicon quantum dots or spin qubits, where we use the spin of a single electron as the state of the qubits, or it could be spin of multiple electrons systems. So these are the qubits that we are actually pursuing at Intel, and this is mainly because we believe that by leveraging our advanced lithography and processing scaling capability, we can actually scale this to a very large number because they're actually small, as we'll see in a second. Then we have topological qubits. These are a little bit more complicated to explain. You might have heard something recently, and these are the ones pursued by Microsoft. I think these are outside the scope of this talk, so I will skip them. And in fact, the focus is going to be around silicon quantum dots or spin qubits. And even though the controller that we've been built at Intel can also operate on superconducting qubits. And in fact, at Intel, we had until 2019 a program on superconducting qubits. And this is the Tangle Lake, which is one of our test chip, which has 49 qubits. So when you look at this, you can probably already see what the issue is. This chip is big. It's almost 4 centimeters by each side, and this is only for 49 qubits. So another way of looking at this, which I like personally, is this one. Here you see a zoomed-in image of one qubit, one superconducting qubit. Again, you can implement them in different forms. This is one of the implementation. And this is drawn to the same scale. Here on the right, you see a full Bluetooth low energy transceiver implemented by Intel Labs in 14 nanometer. So it's clear when you see this that commercial CMOS circuits are much smaller than one single individual superconducting qubits. And so this to us could be a big barrier to scaling this to a really large number of qubits. So now let's go back to the spin qubits. So the other good thing is that when you look at the spin qubits, it really looks like a transistor. So lithography here is a winner. So you can see here, for example, it will have, of course, like contacts, a gate, and an oxide, and somewhere where you form a channel. And so what you do if you have, for example, a linear array of qubits, we expect to see, again, 2 contacts and a set of gates. And then by adjusting the potential of these gates, what you do is you manipulate the potential profile in the channel, and you try to push away all the electrons and isolate just one electron in a single potential well. Of course, this is not so easy as it seems, because you need to be able to control and manipulate the single electron. So you need a very, very well-defined potential landscape and very good purity in terms of spurious charge or any other traps at the interface. So, however, even if you have your quantum well with your electron, you push all the electrons away except maybe one for each of the quantum well, this does not really create a qubit yet, because all you have is a single electron. And we've seen before that to create a qubit, we need a 2-level system. And so to do this, we apply a constant magnetic field. And what this field does, it basically splits the energy between the state of spin down and the state of spin up. And this is called, you might have heard, the Zeeman split phenomenon. And so the gap between this energy, as you can see here, is proportional to the intensity of the magnetic field that we apply with some constants. And so here you go. We applied the magnetic fields, and now we have the 2 levels, one associated, for example, to spin up, and we associate this to the ground level of the qubit, and one to the spin down that we associate to the excited level. And so now we only need to understand how we can manipulate this qubit, or basically how to create transition between the 2 states. And this brings in the key role of the control electronics. So when we look at the full quantum computing stack, as we show here on the right, the control electronics basically sits here between the qubit chip and the qubit control processor. So what the control electronics does is it takes this micro instructions coming from the qubit control processor, and it maps this into electrical signals that are needed to control the qubit. So I like to group this in 3 big categories or groups of signals. So the first one are the signals that we need to manipulate the qubit states, or sometimes I refer to this as a qubit drive. These are RF pulses, and the frequency changes depending on the type of qubit, from few gigahertz all the way to, say, 20 gigahertz. Durations are, again, between 50 to 100 nanoseconds, and they can go all the way to like microseconds. The other group of signals are the signals that are needed to control interaction between qubits, or, for example, to create entanglements. And these are typically, they're like more like square pulses, typically in voltage, because you're controlling like the gates of potential. The dynamic range of these pulses are in the order of like few hundreds of millivolts, and rise times goes in around nanoseconds. And again, the durations are all over the map, depending on your implementation. They can go from like few tens of nanoseconds to even milliseconds in some cases. Then you have to do readout, and there are many ways of doing the readout. The one that we will talk about in this seminar is RF reflectometry. So it looks more like a network analyzer. You're basically sending a CW pulse to the qubit, and depending on the qubit state, the phase and the amplitude of this pulse in terms of reflection will change. And so by detecting this shift in amplitude and phase, you can effectively measure what the spin of the qubit is. And the frequencies here are, in the order of tens of megahertz or hundreds of megahertz, and the durations depends on your SNR. Typical numbers are in the microseconds, I would say. Okay, so now to better understand how we actually use the control signals, I need to introduce the concept of Bloch Sphere. You might have been seeing this before. It's a way of representing the state of a single qubit in a 3D space, as shown here on this sphere, which is a Bloch sphere. And the state of the qubit is basically this vector. So we can say that the North Pole up here is the ground state. The South Pole here is the excited state. And then any point on the surface of this state of the sphere is a pure state. And we can represent it with this equation. You can see this equation is a function of 2 angles, theta and phi. So theta, in a sense, represents what changes when we feed a RF pulse to manipulate the qubit state. So the more energy we provide with the pulse, the more theta will increase. And so for example, we can change the state from 0. We can rotate this vector all the way to 1. Basically, we flip the qubit bit state from 0 to 1. The phi angle is a little bit more difficult to understand, and it tells basically around which angles we want to rotate, and it has an importance in the way that the quantum algorithm is executed. When we measure the qubit, as I said, we only measure 0, 1, or the probability of measuring 0, 1 by doing statistics. And so what we do is we project this vector on the z-axis as shown here. So you see if the vector is here, the projection is 1, so the probability of measuring 0 is 1 because it's always in 0 state. If we have the vector over here, the projection gives a probability of being a ground state of 0. And any point on the equator represents a pure superposition where the probability of having a ground state is 0.5, meaning that the qubit is in pure superposition between 0 and 1. Okay, now that we have this concept, let's look at the quantum algorithm. And I want to use this to walk you through the kind of signals that we need to control a qubit. So here we have two qubits, qubit 1 and qubit 2. They're both initialized in ground state. And then each of these boxes represent a quantum operation. So we do 2 quantum operations on qubit 1, 1 on qubit 2. Then this represents an entanglement or like a 2-qubit operation. And then these are the readout for each of the qubit. And so this is kind of laid in time, left to right, executing the algorithm. So let's start from the first operation on qubit 1. So as we've seen before, we need to excite the qubit to manipulate the state. And so to do this, we need to modulate the magnetic fields nearby the qubit. So we saw we have a static magnetic field that is used to split to 2 energy levels. But in order to rotate the qubit state, we need to manipulate the magnetic field with an AC signal. So what we do is, you can see here, we have a metal line that goes very close to where the qubit is actually created in the quantum well. And we provide an RF current here that generates basically a RF or AC modulation of the magnetic fields nearby the qubit. Now, we have seen before that the qubit has 2 energy levels, one associated with ground state and one associated with excited state, as you can see here. And in this case, delta E1 is the energy gap between these 2 levels. Now, we can write this energy gap as a function of frequency by using this equation, where h is the Planck constant. So this frequency, F1, is the Larmor frequency of the qubit, it is called, and it is basically the resonance frequency of the qubit. So in order to manipulate the qubit state or rotate at angle theta that we saw before, this modulation, and so this RF pulse, has to be provided at the Larmor frequency of the specific qubit that we're addressing, in this case, F1. Then there is the phase of this RF pulse, and the phase of this RF pulse is associated to which axis around the Bloch sphere we want to rotate this its state. And then, of course, the energy, which could be basically the power and the duration of this pulse. And the energy defines how much we rotate the state of the qubit. So I will show here an animation in a moment. And so here you have the Bloch sphere, so that we start from a ground state represented by this vector. And so this is the first operation we want to implement. We want to rotate around the x-axis by an angle equal pi. This means nothing else than basically going from a ground state to an excited state, rotating, in this case, around the x-axis. So in this plot, you see the amplitude of the pulse that we will provide with time. And on the bottom, we see the probability of measuring a ground state. So we'll, of course, start from 1 because we are in ground state, and we'll see how the transition will happen. So if I run this animation, you can see as we provide the pulse, the probability will be moving from, or measuring 0, will be going from 1 to 0. So we basically flip the qubit, and you have seen the rotation around the Bloch sphere. And by the way, this value is nothing than the projection on the z-axis as this vector rotates around the x-axis. So that's what we've done. And to do this, we need to calibrate, of course, the energy of this pulse. So we need to have a specific amplitude and a specific duration such that this rotation basically brings us exactly in the excited state. That's where the control electronics is also, of course, very, very important. Now, if we want to do a second operation, for example, now we want to rotate around the y-axis, and we want to rotate less. We want to rotate by pi by 2, by 90 degrees. So meaning that the vector starting here we want to rotate by 90 degrees, and so we want to end up over here around the equator. So the qubit is the same energy gap, so we will use the same frequency, but now we want to rotate it around a different axis. And so this pulse, if we arbitrarily define the previous pulse as the x-axis pulse, this pulse now has to have a 90-degree phase shift with respect to the previous pulse. So now immediately you see that all these pulses have to be phase coherent, which is another characteristic which is very important. In terms of the rotation, we need like half energy, and so we can either send a pulse which is half of the duration with the same power, or we can keep the same duration. It's nice because it's represent kind of the clock period of our computer, but we scale the amplitude by a factor of 2. And so when I run the animation, we can see half the amplitude, and now we went from the ground state, we went to a pure superposition by rotating around the y-axis, and so we ended up over here. So all good for the first qubits. Now we need to operate on the second qubits. Now the second qubits could be a different qubit, physically and located in a different position. So this gap in energy could be different. This means that also the frequency, the Larmor frequency associated with the qubit is probably different. And this could be just because of fabrication tolerances, or it's something that we are actually inducing. I will talk about that in a moment. So now we need to change then the pulse frequency at f2. And again, the other stuff is rotation around the y-axis. We want to rotate by 90 degrees. So again, we need a specific amplitude that is calibrated. And in this case, we want to use a 90-degree phase. And so similarly to what we saw before, we send this pulse, and now we're rotating this qubit that was in the ground state around the y-axis by 90 degrees. And this is basically what is in terms of the single qubit gate operation. Okay, now let's say we want to do this two-qubit operation that is shown with this symbol here. So in this case, we're doing a controlled knot or C0, and all it is the quantum equivalent of an XOR operation. So we have a control qubit, in this case Q1, and so if the control qubit state is 0, the state of Q2 will be unchanged. If the control qubit is 1, the state of Q2 will be flipped after this operation. So this is basically two-qubit interaction. So how do we do this? So here in this cartoon, you can see we basically place the two qubits, Q1 and Q2, nearby in two separate, say, quantum wells. And we start from a situation where we have very large potential barrier here. And so these two electrons are isolated, they're not interacting. Then to implement this gate, what we do is we use a DAC, high-speed DAC, to lower this barrier for a specific amount of time, let these two electrons interact between each other, and then we raise back the barrier to, again, keep the electrons separate. Now, in order for this operation to be executed properly, we say with the good fidelity or like low error, if you want, this pulse that makes the two qubit interacting has to have a specific amplitude and a specific duration. Now, when we look at this digital to analog converter, typically they have these pulses are in the order of a few hundreds of millivolts, and we need at least 10 or 11-bit resolution, or of course, potentially even more. And in terms of noise, the typical values that we need here are related to the LSB and dynamic range, of course, but we're talking in the order of like a few tens of microvolts RMS. So one interesting thing that I would like to bring up for the drive is that we saw that the two qubit had specific Larmor frequencies. And so one interesting aspect there is that potentially we can use the same RF line to excite two or multiple qubits by operating in frequency multiplexing. So this is like your cellular network where you have different channels and you can use the same medium or the same channel, meaning air, but each user is associated with different frequency. And so this way of using frequency multiplexing is actually very, very key to our implementation, because it's a way of allowing us to reduce the interconnect, because we can multiplex several qubits on the same RF line. Okay, so now we need to get to the readout. And so to do the readout, we need to measure the spin of a single qubit. And of course, this is extremely challenging. So we need to find a way of measuring something that we know how to do, for example, charge. So we need to do what is called a spin to charge conversion. How do we do this? So what we do is we place the qubit that we want to measure, so the quantum dot, close to a reservoir of electrons. So this is basically an ohmic contact. And you have a reservoir with the EF being the Fermi level. And in the dot, as we know, we have the two energy levels, one for spin down and one for spin up. So what we can do is we can apply a potential to the dot gate, so V dot in this case, and we can increase this potential such that the Fermi level is exactly in between, or approximately in between, the spin down energy level and spin up energy level. And this is where the magic happens, because if the spin is down, now this energy is lower than the Fermi level of the reservoir, and so this electron won't be able to tunnel into this reservoir. So no charge displacement or movement will happen. However, if the spin is up, so if the electron energy is here, this is high enough, is higher than the Fermi level, and so this eventually will tunnel with a probability that can be adjusted into the reservoir, emptying this dot. And then since this dot is empty, now one electron with the spin down will jump into the dot. So for this case, we have actually physical displacement of charge from the dot to the reservoir and back to the dot. And so we can detect this charge movement. And we do this with a very sensitive charge amplifier, a single electron transistor, because we can do this at very low temperature. It's an SCT. So we couple the gate of the SCT with this dot. And so and we monitor the current through the channel. So whenever we have a transition of this charge, the gate of this SCT will be modulated, and this will also modulate the channel resistance or the current flowing through this SCT. And so only when we have a spin up, we will see basically a pulse in the channel resistance, if we're measuring resistance, or the current of this SCT. So this is a way of converting something very difficult to measure, the spin, to something that we can actually measure, which is a charge, or in this case, a current. Now, this measurement is a direct measurement of resistance or current, so it is sensitive to low frequency noise, so 1 over F noise of your amplifiers or any electronics that you use. So it can be challenging, and your SNR can be affected. So another way of doing this, which I mentioned before, is measuring the channel resistance indirectly using RF reflectometry. So what we do is we basically build a matching network here to match this impedance, which is typically in the order of tens of kilo, to our 50 ohm line coming in. And then we send our pulse, and then using this coupler, we split the reflection. And so the reflection of the gamma coefficient is also modulated by the channel modulation. So in case we have this modulation, we actually see it in the reflected signal, both in terms of amplitude and phase, because gamma, of course, is a complex quantity. And by using a coherent receiver, we can actually demodulate this and effectively detect if the spin is up or down. Now, again, if the qubit theory is superposition, we cannot do this in one shot. We need to do this measurement over and over and then collect statistics. The advantages here is that we're operating in RF now, or like hundreds of megahertz, so we are away from flicker noise. We can benefit from higher SNR. The disadvantage is that now we need to implement a very IQ matching network here, because the impedance transformation ratio is very high. And typically we use superconducting methods to do this, but it can be bulky. So there are some drawbacks here. Okay, so now that we know the basics of control, does this scale? So let's take an example here of, say, 3-spin qubits chip. So assuming that we do this very smart frequency multiplexing and say we only have one line that brings direct pulses to all the qubits, we still need to control all the gates between the different qubits. And you can see here an actual microphotograph. And we need at least another 7 signals for this. And then we need, say, at least 3 signals to do our readout for the SCT. So it is clear that if we want to scale this to 1,000 qubits, we need several thousands of coax lines. And so since also you probably know these qubits, specifically the spin qubits, since they're very fragile, they need to be at extremely low temperature in big dilution refrigerator and actually sit at temperature that are in the order of tens of millikelvin. All these cables has to be routed from the external control electronics into the fridge down to the qubit. And this clearly doesn't scale. First, because of the sheer form factor of the coax cables. Each cable is basically pumping heat into the fridge, so there is a thermal load to the fridge, and the power consumption, of course, and the cost of all the room control electronics at room temperature. So how many signals do we need? Well, too many. And here you can see a setup from Google that was used to control about 50 qubits. And now this image clearly says that the control electronics and the interconnect to control electronics can clearly be a challenge in order to have a large scalable quantum computer. So it's clear that we need more integration. And so we have been tackling this by proposing OR-Switch, which is a highly integrated cryogenic qubit control. So you can see here where we are with the classical implementation. We have the control electronics sitting outside the fridge, as I mentioned. And then we have all these cables going into the fridge down to the qubit chip, which sits in the millikelvin stage. And these are not just cables, but there are like attenuators, filters on each line. Because, for example, any signal generated here at room temperature carries a 300 Kelvin thermal noise. And so in order to operate at 20 millikelvin, we basically need to take this 300 Kelvin noise, and as we go colder, we need to keep attenuating this noise until we bring it basically below or at the same level of the thermal noise at the temperature where we're operating. And so for this, we need attenuators along these lines. And so what we want to do is we want to take this control electronics and push it inside the fridge for now at the 4 Kelvin stage, where we have about 1 to 2 watts of cooling power. And so we can implement meaningful SOC. And now you can see the interface in and out the fridge is a high-speed digital interface, so much less sensitive to noise, and we can actually benefit from the typical scaling of digital I/O. Now, of course, this interface between the 4 Kelvin and the 20 millikelvin stage is still very challenging if you want to scale to a large number of qubits. And what I see here is that in the future, we will either have additional control electronics in the millikelvin stage, as already shown by other people in literature, or eventually the two systems will meet somewhere in the middle, say at 1 Kelvin, where we can actually leverage co-packaging integration technique to solve this additional issue. Okay, now that we know, we see that in order to control qubits, we need high-speed RF signals. We need basically coherent receivers, high resolution, high-speed DAC, and so it's clear that there are lots of challenges in order to implement an SoC that also has to operate at cryogenic temperature. And the first thing to do is to enable a system on chip, design at cryogenic temperature. So this means that we need to have the usual tools, device models, both analog and maybe RF models, models of the passive, all validated at cryogenic temperature. We should also have a corner of our standard cell library characterized at cryogenic temperature so that we can do digital design and close timing. The other important part is that we need to understand what the signal specifications are. So we're not designing a radio for a specific LTE standard. Here we're trying to, we need to understand what is good enough to control this qubit with the required fidelity. And today, if we just take the big boxes that are used for the external control electronics and we try to just integrate them in the SoC, we will immediately run out of power budget, and for sure the solution won't scale. So we really have to understand what trade-off we can take and understand what are the minimal signal specification to achieve the required fidelity in the control. And this is an optimization that has to be done across the full stack, because if we have constraints in the way we control the qubits, we need to see what implications on the full stack these constraints creates. We then need to have a fully scalable architecture because we want to scale this to a very large number of qubits in thousands or more. And we also need to address other problems like packaging at cryogenic and the integration in terms of mechanically and thermally integrate these PCBs and this system within the fridge, which of course they're not trivial. So I believe that as Intel, we have a strong competitive advantage because we have created the right blend of RFIC and mixed signals and quantum core expertise. Today we can implement this cryogenic SoC with more than 10 million transistors with both RF and digital integrated, and also do direct experiments on qubits in the fridges. And we're also leveraging our communication theory expertise on digital signal processing and algorithms that we can borrow from, again, the communication theory. And this, for example, can be used for frequency multiplexing in order to apply filtering to the pulses. And so try to use filtering to reduce the crosstalk in the control. And so in the end, this translates to a more denser integration of your qubits, for example, in terms of number of qubits that you can control over a single RF cable with a specific bandwidth. And then we also have strong expertise in packaging and interconnect, which, as we've seen, is key to move forward to the next step. And last but not least, we're using our own Intel 22 nanometer FinFET technology. And so we have leveraged our device modeling team to have silicon verified cryogenic models, as I said, both analog and RF for our 22 nanometer FinFET process. And we also have a cryogenic corner for the standard cells so that we can do digital design and timing checks. And in the future, we can also see the possibility of optimizing a specific flavor of the process in order that to squeeze even more performance out of these devices at Cryogenic. Okay, so this is a very brief summary of our first SoC, Ostrich 1. This one was focused on the drive capability, basically generating the RF pulses. As I mentioned before, this was targeted both the superconducting qubits and also spin qubits. And the main feature are listed here. It has basically 4 different transmitters, and each transmitter could generate 32 frequencies using DDS synthesis and frequency multiplexing. So over 4 cable, potentially we can control 128 qubits. The pulse shape of the RF pulse can be arbitrarily generated with arbitrary envelopes stored in an SRAM, and this is used to implement all the different operations as we've seen on the qubits. And we have a wideband frequency output to cover different type of qubits. Here you can see the fridge, the cryo PCB with the packet chip. Then we have our IC, microphotograph, and the qubit chip would sit at the end here at the 10 millikelvin stage. And this is our 4 Kelvin stage. So here you can see an example of a measurement done while Ostrich 1 was at cold at 4 Kelvin. We're generating, different pulses with different envelopes, different frequencies, different duration. And here you can see the time domain representation, and here the frequency domain representation. Now, this is just to show the extreme flexibility of the IC in generating all different shapes and different pulses, and also how frequency multiplexing is actually implemented and is key to enable further scaling in the control. Of course, we also tested Ostrich with actual qubits, and here we see the experiment of measuring the Rabi oscillation of a single qubit, spin qubit. Now, let me explain for a second this experiment. What we do here, we start from a qubit which is in ground state, and then we provide a pulse to rotate the state of this qubit, as you can see here on the Bloch sphere. And we do this experiment many, many times. At the end of each pulse, we measure the state of the qubit. And we repeat the experiment, and as we repeat the experiment, we increase the energy of this pulse. So as we increase the energy, as you can see, every time we rotate the qubit more and more, and so eventually we would reach the excited state. And then if we further increase the energy of the pulse, we will go back to the ground state. So when we collect statistics, if we plot the duration of this RF pulse as a function of, say, the probability of measuring an excited state, what we'll see is oscillation. So no pulse, ground state. As we increase the duration, we start moving to the excited state, and then as we keep going, we will rotate back basically all the way to ground state. So this oscillation means that we can coherently control the qubits with our RF pulses. Now, the reason we don't see this oscillation going between 0 and 1 is because the readout mechanism itself as an error, and so this error basically reflects in an attenuation of this range of oscillation. And we have recently demonstrated that we can get exactly the same gate fidelity using Ostrich as what we can get with external control electronics. And this is a very important milestone, and the results of this work will soon be published in Nature. Okay, our second SoC, which was presented at SSCC this year, is shown here in terms of block diagram. So here we target specifically spin qubit, and we extended the capability of the controller to all the other functions. So we have drive, where we can control 16 channels and frequency multiplexing from 11 to 17 gigahertz with fairly wide power control. But we also have RF reflectometry using for the readout. So you can see here we basically have a multi-tone transmitter and the receiver that we use to measure the reflected waveform. I suggest, of course, to go and look at the reference. And then we also have 22 DACs with 11 bits that we use to pulse all the different gates potential that are in the qubit chip. Other feature that we have here, we have implemented a digital FIR on these pulses to be able to do this filtering and improve the fidelity. We have integrated a microcontroller so that we can have more flexibility in the way we execute the algorithms. And we also have temperature sensing, because it's very important to know what the actual junction temperature is, because it can change your thermal noise by a factor of 10. If your junction is 40 Kelvin instead of 4, for example. Here you see some pictures. This is the chip microphotograph with the different areas highlighted. This is the PCB, and then this PCB is sandwiched between these two copper flanges that creates good contacts also to the back of the silicon here with these indium springs. And then this is assembled in the fridge and 4 Kelvin stage as seen here. So where we are today, we have demonstrated the functionality and performance target, both at room temperature and 4 Kelvin. And we're in the process of integrating this in the fridge with the qubit samples to effectively demonstrate that we can replace all the external room temperature electronics by using this SoC. And here you can see like an experiment, a simulated Rabi experiment where the SoC is generating the different control signals to do that Rabi experiment that I showed you before. So pulses with increases energy and read out after each pulse, and then in this case just 2 channels of the pulsing that is needed while you do the readout. In terms of performance summary, I don't want to spend too much time here. It's more for reference, but the key takeaway here is that as far as we know, OrSwitch 2 is the only system out there that is able to implement all the 3 functionality to control spin qubits. Okay, moving forwards, we're not nearly done with the control. So first of all, we still don't have a fully scalable solution. We need to be able to have a solution that can scale within that power budget to large qubit arrays, and also work on the qubit arrays, like 2D arrays of qubits as well. We need to develop additional cryogenic analog RF IPs, like, for example, PLLs, references, crystal oscillators that will go into and complement the other function in the SoC. And then we need to work on interfaces. Both interfaces, the one from outside the fridge going to the OSPC, and this we said it's a digital interface, but depending on the number of qubits and the complexity of the computer in the future, the bandwidth of this interface might become very challenging. And then the other interface going from the control down to the qubit. And here, as I said before, we need to find a way of scaling that interconnect using a log n, where n is the number of qubits. And so we can do this by doing some sort of row and column addressing with electronics integrated with the qubit chip. Or at some point, we can merge the two in some way in the middle, for example, operating at 1 Kelvin, where we can still have a decent qubit operation and we have enough cooling power such that we can implement meaningful control operations. So and this brings me to the conclusions. We have seen basically the controlling qubits require high precision RF analog signals. And we have today many quark cables going into the fridge. And so the current approach does not scale. So with our switch, we have Intel first integrated cryogenic qubit controller. And we believe that with this, we will have the first step towards the scalable quantum computer. And that's all. Thank you.
All right, thank you, Stefano, for that. So I will, I guess, moderate questions from the audience who can't unmute themselves and go through you. So if you have questions, please post them in the Q&A panel, I guess down on the bottom of your screens for that. So with the first question from Mark Hoffman, could quantum computing be used for Bitcoin generation?
I'm probably going to not comment on that questions. I probably don't have enough experience to give you a meaningful answer. I don't think I could say. Yeah, it probably is probably related to the way the Bitcoin generation algorithms are implemented. So in any case, anything that has a benefit from an exponential complexity, anything that has an exponential complexity that can benefit from this, the superposition that we get in quantum computing, I think it could have a benefit from this. imagine, the typical problem of the travel salesman, or the factoring problem for prime numbers. But yeah, I probably don't have enough understanding of that to give an answer. Sorry.
Yeah. Okay. So the next question, so from Cliff Chan, what is the coherence time of the spin qubit?
Okay, that's a very good question. So if we have been using purified silicon, so or silicon 28, which enables us to remove the coupling to the spin, the nuclear spin of the isotope, and we have achieved and measured T1 times in the order of seconds, which is actually very good. So the T1, you can see this as the spontaneous relaxation time. So basically, you take the qubit, you put the qubit in excited state, and then you wait and you see, how it decays to the ground state. However, the other important coherence time is the T2, which is the coherence time of the qubit, meaning how focused or how coherent you can be with the qubits with respect to your control. And by using like T2 star measurements, we've been seeing hundreds of microseconds of coherence time. So again, very, very good numbers in terms of also the speed at which we can operate the gates. Because again, what is important is the ratio between your coherence time and your gate time. Otherwise, if you have a long-lived qubits, but your gates are very long to execute, you still cannot do very much with the computer.
Okay.
Yeah, I recommend anyhow to go and look at the reference of the papers that have been published in collaboration with Q Delft for the details.
Yeah. So next question is from Christoph. Does the Bloch sphere imply that the different quantum states are always in a fixed coherent phase relation?
Let me go. So let me try to see if I understood the question. Probably there's no need to go there to the Bloch sphere. So the way you can see the qubit is, again, as we said, is an oscillator. So the oscillator will basically have a frequency, and it has its own phase. So when we want to control the qubit, we need to basically do this in phase with the qubit. So the moment we pulse our RF signal, we need to be able to pulse a signal with a phase that is in phase with the qubit. Because, for example, if you are in phase with the qubit oscillation, you will say rotate in one direction on the Bloch sphere. But if you're out of phase, it's like applying a negative pole. So you would rotate in an opposite direction. So I don't know if this analogy might resonate with you or not, but in a sense, I see some analogy when, for example, you want to kickstart a high quality factor oscillator. What you do is you want to provide energy at the right frequency, but you also have to be with very specific phase, because if your phase is off, instead of providing energy, you will absorb energy, and you will not do what you really want to do with providing energy to the resonance. I don't know if this answers your questions. I'm not sure I understood what you mean for saying that all the state have to be coherent, if you meant with respect to the control or something else.
Yeah, so Christoph, if you want to sort of chime in the chat and see if that sort of answered the question in there, if you're still in there, let's see.
See if I can turn on the chat.
Ah, okay. In the questions, yes, this question has been answered by the existence of the that. Okay, let's see. Next question. For entangle of multiple bits, would a 3D approach be more appropriate?
So yes, I mean it's very important that we have a way of entangling potentially all the qubits, and so this is a matter of connectivity. if we have isolated qubits, of course, we cannot build a quantum computer because we don't have, for example, a CNOT gate where we can have interaction between two qubits, which is something that you need for your to build your quantum logic. And so what you can do, for example, in a linear array, you would have neighbor qubits that can be entangled. And then what you can potentially do is, if you want to entangle different type of qubits, you can shuffle the qubits around, almost like you would do with the charge in a CCD sensor. And so you could shuffle the qubits around and eventually lower the barrier that creates this entanglement between the two qubits, and then move the qubits that have been entangled in a different position, and then keep repeating this. However, this requires additional operation, this shuffling, which goes against you, because as we know, the qubit has a specific decoherence time. So the ideal would be to have basically, if you think in terms of 2D space, would be to have all the qubits somehow interconnected with each other. But this is very challenging. It's very challenging in terms of implementation, because as you can see, you can see that you could, in a 2D grid, you can have neighbor entanglement, but creating a full net would be very demanding in terms of the interconnect. And so today, people are exploring some hybrid approaches where, first of all, you for sure you don't have a 3D, because remember, you need to confine the electron in a specific quantum well. So if you want this to do this in a 3D space, it's very difficult, because you realize the well by using potential in one direction, a trench maybe in another direction, and then you have a thin layer of silicon between, say, silicon germanium, where you confine in the Z dimension. So creating this in a 3D space would be very, very challenging. But even in the 2D space, people today are not, they cannot have a full connectivity in terms of qubit topology. And so they're exploring different topology of connectivity. For example, a ladder connectivity, where you have two arrays and then you have some connections across the two linear array once in a while, or like forever qubits. And you can see these are like diagrams that are published in implementation. I know that, for example, IBM have shown some of their connectivity solution, and all it is a very delicate balance between the complexity of your interconnect and the complexity of the control and the constraints that you put in your algorithm execution, because you need to do extra operation in two qubits together and do, for example, an entanglement there. So this delicate balance is what I refer to like a full stack optimization, which is very, very challenging, because the search space is very large and it's very interdisciplinary. So it's not so easy to move forward, as you can imagine.
Yeah. Okay. So question from Jeff. So speaking about process technology, will or would FDSOI process offer better control for a single electron quantum well?
Yes, there's been some interesting work in FDSOI in terms of creating what's called a single electron device, or show, for example, Coulomb blockade, meaning that you can show this discrete energy level, and you can see that in a quantum potential well you can load single electrons, but from there to actually have a qubit with the decent decoherence time. And also with two separate levels, saying, for example, if you want to use a spin qubit, I think that's it's very challenging when a conventional process is used, like if you take your commercial FDSOI. So yes, I believe you can show like a Coulomb blockade operation for a single transistor at low temperature, but from there to go to a reliable qubit operation, there's still a lot to do. And issues that you can have is that you can create, for example, spurious dot in places where you don't expect to have dots, and so you have basically qubits located where you don't want them, and then it's very difficult, for example, to entangle two qubits if you have parasitic qubits. And there are other problems related to impurity of the interfaces, and so actually I didn't go into the fabrication details, but there's a lot of work that needs to be done, and this is happening today in order to be able to have a process that is still compatible with, say, 300 millimeter wafer lithography, but that gives the required purity and control to be able to create this very clean interfaces. Because this is a very small charge, so all you need is a defect somewhere that introduces a charge that is not stable and maybe moves under electric fields, and this can disrupt your whole system. It's a very interesting area of exploration, because it would allow to build circuits and qubits on the same process, but I think there is still a lot of work to do. So
Okay. Yeah, so let's see, next question. So I think to the qubit operation. So did you create a Bell state using your CNOT? And what is the purity achieved?
so we have the details of that in the paper that is going to be published in Nature. So I'll probably defer that when the paper will come out.
Okay. Yeah. See, and we have one last question here from David. Does your work result in a general purpose quantum computer or controller, or does each problem need a different IC?
So let me see. Sorry, let's see if I can jump on the slide. Yeah, so for Ostrich 2, we have basically a single SoC, and this can cover all the functions. So we have a drive section where we implement the RF pulses to manipulate the state of the qubit. We have this section where we do the readout. So this is basically a network analyzer. We send multi-tone signals. There is a reflection here and the circulator, and then we detect the received, the phase and amplitude shift of the received signal. And then we have all this DAC to control the gate potential. So with this, we can cover basically almost the entire control signals needed to control a linear array of, say, depending on how you do your gates, we have like 16 different frequencies here, but maybe we don't have enough DACs here to control 16 qubits, but you could say at least say seven qubits in terms of linear array. The only thing that is not included here is the DC bias of these gates, because right now often voltages say higher than even like 2 volts are used, and so this is not easily implemented in a scale technology because of high voltage needs, but we are also working on it. So the answer is, yeah, I think for a smaller system, this SoC can take care of everything. As I mentioned before, when we want to scale this to a very large number, we probably need to add an additional very low power kind of mux-dmux circuit here, chip, and this could be again co-packaged with the qubit chip, or maybe in the future we will have the possibility of having some very basic like switch, like a HEMT transistor as part of the qubit process, and then you could see this as like building a memory where you have your qubit, you have your raw column decoder in the same chip, and then this creates an interconnect scaling with a logarithmic in a logarithmic way, and this will allow this to scale to a very large number. But yeah, this in theory should be able to take care of all the problems for a small array of the control required.
Yeah, so we've had a couple more questions come in. So we'll go with this one first, since we're talking about sort of scalability. So from Colin, so you mentioned that you might be able to take advantage of QNNs with as little as 1,000 non-error correcting qubits. Are QNNs less susceptible to noise than more taxing computations like Shor's algorithm?
Sorry, I think, is there a way I can look at the question, or maybe can you repeat the question briefly?
So with say 1,000 non-error correcting qubits, you mentioned that you could take advantage of like a quantum neural network.
Yes.
So are quantum neural networks less susceptible to noise than computations like, say, Shor's algorithm?
Oh, okay. Yes. I think again this is a little out of my expertise. We have been doing some work on quantum neural network. We have a team in Intel Labs that works more on the computer architecture and the algorithms. So I will be very happy to follow up on your question if you send me an email, and I will put in contact with the right person. You know, one thing about the quantum computing space that I've learned is that it's very wide, and if something you don't know, you just don't answer. But yeah,
Okay.
please send me an email that I will follow up with your question.
Yeah. Let's see. And then so two questions here. So for someone with a background in electrical engineering, what is the best way to get started on quantum computing?
Oh, so the first thing to say would be don't be afraid. There is a lot of contribution that I think EE can do with a very basic understanding of what the problems are and basic understanding of quantum computing. You would be surprised how once you understand the basics, there is a lot that you can do without the need to go into really, like, you know, deeply into quantum mechanics. I spent most of the time at the beginning when we started a collaboration sitting, you know, side by side to the people working on the control, and the experimentalists try to understand what was done. And I think the biggest challenge for me has been the language. The same concept are seen under different perspective, and so they will not talk to you about dBm for the power of the pulse, but they will tell you a specific number of photon that the pulse has. And so I think there has been already a lot of work bridging these two area, and now with that I think there is already, for example, a clear idea or understanding of, for example, what is needed if you want to control superconducting qubits in terms of, you know, the purity of your RF signal, the frequency range, the phase noise, and so understanding this basic specification already allow you to work on the electronics potentially, which I think is very important. The other aspect is the system partition. How much intelligence do you put in this SoC, because the power budget is limited? How do you partition your system based on the needs in terms of latency? There are some things that you want to do, for example, error correction that needs very low latency, and so maybe that part you want to have it on your digital backend at Cryogenic, but maybe there is other things that you don't want to have it there, and you use, for example, a memory outside at room temperature where you don't have power constraints, and maybe you can have access to larger memories. So this part, in terms of more on the quantum of the computer architecture, there is also a lot of work to do. And yeah, and then again, we take this system. There's still a lot of work if we want to scale this to 1,000 qubits. So optimizing the design in terms of power consumption, and doing something smart, partitioning this chip with different function that operates at different temperature, or you have different power budget. It's also quite interesting. But you know, my advice would be don't think that you need to know everything about quantum computing before you can make a difference. There is a lot to grab out there.
Okay. And it looks like we have one final question. And so what are the current challenges in implementing cryogenic analog RFIPs?
In terms of specific cryogenic design, if we don't think in terms of like the limited power budget of the fridge, I think one challenge is that maybe the modeling environment is still not complete. For example, we don't have yet high volume data. So we don't have, for example, mismatch models. And this can be a problem because the mobility increases. So all your devices are pushed deeper into subthreshold. And there are also some very specific physics that can happen at low temperature that also depends on the process. Typically a highly doped process, which could be like a more scale process in you know the tens of nanometer, it behaves similar, say, to a behavior at room temperature. But if you look at papers, there are people that have been reporting specific effects where they call it kink effect, where because of the substrate freezing, you start having some very abrupt modulation of the threshold voltage. So I think there has to be some very extensive and methodic modeling work, and yeah, and then once you have a good modeling capability, and this also, by the way, includes also the electromagnetics, because you have to know what the substrate resistivity becomes at this temperature. You need to know what the conductance of your copper lines and the rest becomes, so that you can actually estimate, say, the quality factor of your resonance network, for example. But once you do that, then it becomes, I believe, always a challenge in terms of the power budget being limited if you want to scale this to a large number. But then I don't see a specific challenge to cryogenic. So I think once we get good models, I think in terms of design, there is a lot that we can achieve.
Great, thanks, Stefano. Yeah, that seems to be all the questions that we've had so far. I would like to, thank you again for giving us this presentation and spending the time here. And if we could, I would tell everyone to give you a nice round of applause and doing that. So.
Yeah, thank you. And I want to apologize for not being able to answer all the questions. As I said, this field is very wide. But again, feel free to reach me, and I can put you in contact with the proper expert. We have a big team working on this, and because you need all different type of people. So.
Yeah. All right. Thank you.
Okay. Thank you, everyone. Bye.